Good morning, good afternoon, everyone. My name is Monserrat, and I will present our work entitled Development of Bismuth oxychloride doped with copper oxide heterostructured materials supported on zeolite with photocatalytic activity under solar irradiation for the removal of recalcitrant organic compounds. As an introduction, water pollution by recalcitrant organics is a serious environmental problem. Methyl orange, for instance, is a toxic mutagenic and carcinogenic monoacetate that resists conventional treatment. Heterogeneous photocatalysis offers an eco-friendly way to degrade such compounds. Bismuth oxychloride shows a good UV activity, and copper oxide doping extends absorption into the visible range. Supporting this on zeolite was expected to improve performance by enhancing surface area, dispersion, and active site accessibility. Our goal was to synthesize a hierarchical bismuth oxychloride doped with copper oxide supported on zeolite photocatalysis and evaluate its performance for the photocatalytic degradation of methyl orange under simulated solar light, using statistical optimization of pH and catalyst dosage. We synthesized the following. First was copper oxide via the solvothermal method. The second synthesis was bismuth oxychloride doped with copper oxide, incorporating 0.6% copper oxide into the bismuth oxychloride. And the third was bismuth oxychloride doped with copper oxide supported on zeolite by adding zeolite according to the experimental design. We applied a composite central design to assess the effect of pH and catalyst dosage for the bismuth oxychloride doped with copper oxide composite. Photocatalytic tests were conducted under simulated solar irradiation. Methyl orange concentration was monitored via HPLC, and we used XRD, FTIR, and SEM for the characterization. The response surface analysis indicated that acidic pH and moderate catalyst dosage yielded the highest methyl orange degradation. And also, the XRD confirmed the coexistence of bismuth oxychloride and copper oxide in the heterostructure with high crystallinity linked to the better photocatalytic activity. FTIR spectra showed bismuth and chloride, copper and oxygen, and carbon and hydrogen vibrations, confirming functional groups. And also, we have that excessive dosage decreased performance, likely due to vertical agglomeration or lake scattering. The scavenger test identified hydroxyl and superoxyl radicals as the main active species. Regarding to the zeolite type, CBA121 achieved 33% removal, while 40 reached 20%. However, and this is important, the zeolite-supported catalyst did not surpass the performance of the unsupported bismuth oxychloride doped with copper oxide in our preliminary results, as the same image revealed microspheres and plates well dispersed and the morphology differences when supported on zeolite. These possible reasons of lower zeolite performance may explain this: the dilution effect, the active sites of bismuth oxychloride doped with copper oxide content per unit mass is reduced when supported, lowering the number of photogenerated charge carriers. Or the non-optimal dispersion, maybe aggregates or thick layers of zeolite can block light and penetration and active sites, which may explain the lower degradation, and the light scattering. The zeolite particles may reflect or scatter light, reducing photon absorption by the active phase. And for the end, bismuth oxychloride doped with copper oxide heterostructures show promising activity under solar light, with degradation strongly dependent on pH and dosage. hydroxyl and superoxyl radicals are the dominant species in middle-range degradation, and zeolite support did not enhance performance under current conditions, likely due to dilution and mass transfer limitations, and the future work will optimize support properties and deposition parameters to overcome these limitations. As an acknowledgement, we thank Anit Fondesit and Smart BRN for funding and access to the characterization platform. Thank you very much. Thank you for seeing this presentation.